Today, because we're just introducing Python, we've got a very kind of basic physics topic to lead us into variables, arithmetic, and input-output in Python. So that's what I'm going to discuss here, and that's the assignment. The homework assignment is really about using the basic functionality, variables, arithmetic, and input-output to solve the assignment. Okay, so I wanted to just talk about, we've got one slide on Galileo's threefold law, and there's another slide on Newton's universal gravity, and then I've got a third slide, just because we think it's highly working in the sort of 16th century on Einstein's general theory of relativity. So if you went back, 1,000 years, 2,000 years, there was the idea that heavy objects fall fast towards the ground and light objects fall slowly towards the ground. And it's a very sensible idea, right? Because if you have a feather, right, you drop the feather, then it falls slowly towards the ground. And if you jump out of a plane without a parachute, then you, as a heavier object, fall much more rapidly towards the ground. So it's sort of based on, observations in that sense, that heavy objects fall quickly and light objects fall slowly. What was the huge breakthrough of Galileo was to this sort of abstraction that in the absence of the atmosphere, in the absence of the effects of the atmosphere, in the absence of drag due to the atmosphere, that all objects fall to Earth with the same constant acceleration. So the feather, in the absence of atmosphere, the feather and you or I, or whatever object would fall with the same constant acceleration. This is the beginnings, this is the birth of computational physics. So at this moment, so this is why I'm doing this at Dom. At this moment, we could start to calculate things like we could calculate the distance fallen in a certain amount of time, or we could calculate the time it takes to fall a certain distance based on Galileo's free-fall law. And so we'll write a code to do that. In the homework, so I'm going to do the free-fall law as a Python example. In the homework assignment for the class, you're actually going to look at what came a little later, which is Newton's law of universal gravity. So what Newton recognized was that say if you drop a terrestrial object, an apple towards the Earth, it's the same force of gravity that's pulling that towards the Earth that's causing, say, the moon, as it orbits the Earth, to accelerate towards the Earth. And by unifying that terrestrial celestial motion, he was able to come up with the law of universal gravity, that all objects with mass interact with one another through gravitational force. They all interact with one another in proportion to their masses. They experience gravitational forces in proportion to their masses. And those forces between massive objects depend on the inverse square of the separation between the objects. So that's Newton's law, universal law of gravity. That has a consequence. That law has a consequence or a signature for the motion of satellites, for example, the motion of the planets around the sun. That inverse square law predicts a characteristic corresponding relationship between the period of the orbits of the planets and the radii of the orbits of the planets. And that's this law here. So this is this law was predicted by Newton's law of gravity. that the square of the period of the planetary orbit is in proportion to the cube of the radius. That had already been uncovered from data by Kepler, so it explained Kepler's third law. So the homework assignment is about this relationship here. So I'm going to solve the problem of how far something will fall and how much time, or how much time it takes to fall a certain distance. You're going to look at the relationship between the altitude of a satellite orbiting Earth and the period of that satellite as it orbits Earth. Okay, I put this in because, you know, the Newton's law of gravity, Galileo's law of free fall, they're kind of hundreds of years old now. But they were really the foundations of a modern understanding of gravity. And a modern understanding of gravity is really rather interesting. So the first point is that there's a class of forces that we call fictitious forces. Fictitious forces have the characteristic that they depend on an object's mass. An example, the classic example of a fictitious force is, you know, if you're in a car going at high speed around a curve. So you experience, you as the driver of the car or the passenger in the car, your experiences of a centrifugal force that's throwing you outwards from the car. Now that's a force that you understand is a fictitious force. There's not actually a real force that's throwing you out. It's just that you're in a reference frame, a non-inertial reference frame. You're in an accelerating reference frame. And that's the reason that you feel or experience this centrifugal force. From an inertial reference frame, there is no such force. I mean, there's a centrifugal force that's exerted by the road on your tires to keep the car turning in a circle, but there's no centrifugal force. So the gravitational force is actually like that centrifugal force. It's a fictitious force in the same sense that the centrifugal force is a fictitious force. But the gravitational force, if you were in, we experience the gravitational force because we're in the Earth's reference frame. But if we were in a free fall reference frame, if we were just falling in absence of air towards the ground, we'd experience no gravitational force. So it too is truly a fictitious force. And all this is built on the fact that the gravitational force is a force that depends on an object's mass, which is just like the centrifugal force depends on an object's mass. And that's a characteristic of a fictitious force. So the simple problems we're doing with the free fall law today, and that you'll do with Newton's gravitational law in the homework assignment, they really were the foundations for a much deeper understanding of what gravity is. Gravity is actually that mass kind of grips space-time and curves space-time, and then space-time, curves space-time, grips masses and determines the motion of masses. And the gravitational force is really not like other forces of nature, electric force, magnetic force, nuclear forces, in being transmitted through space. It's really actually a distortion of space itself by matter, and it's space itself determining the movement of matter.